It's good. It's nice.
Okay, our next speaker is Dominic from the University of Cambridge, who will also be talking about effect systems, but instead he'll be talking about embedding effect systems more generally in Haskell.
Thank you very much. Can you hear me okay?
Is the thing?
Sorry. Yes. Better?
Yep.
Excellent. So this is joint work with Thomas Parametric, and all of the code can be found online by this getting this Cabal package. So who here likes programming with effects? Hands up. Yeah, quite a few people. Oh, some people really like it. Who likes programming in an imperative programming language? Less people. Good. This is what I hoped. So we all want to program with effects. Well, maybe about 75% of us want to program with effects. And we want to use lots of different effects at different times. But because we're functional programmers, we want to do effects in the right way. So we want to control when our effects happen. We want to understand the scope of our effects, where they spill out, and what's going on. So we want to know a little bit more. We don't want to use just an imperative programming language where effects go all over the place. So we can use monads. We might have some program like this where I get some states, and then maybe I have some more states where I have to use a monad transformer, and then I put into this buffer. So here I'm just I'm reading a name, reading the buffer, and then appending that name to the buffer with hi. So I'm using monad transformers because I have two kinds of states. So I get this type, which well, this is one kind of type you can get for it, which is okay. But then if I start adding more state or different monads, and I have to keep adding lifts and lifts and lifts, then it all gets very complicated, as Tom was also saying. So as I'm sure you'll know, monads don't compose very well together. But I'll say something else. The information they give us is often quite low. They're a bit sort of binary. So we look at the types, and that's a little bit like an annotation that tells us what effects are happening. They might tell us the kind of effect, like state, but they don't tell us that much. So we only get the name. We don't put this name state, but we can't tell from the type. We can't tell from the outside. So what's going to happen in this work is we're going to have something a little bit more flexible by using effect systems. So I'm going to introduce a way of putting variables into the program. That's this var constructor, and I'll explain that. And so we can rewrite the program like this and get this new type, which is it's like a set, and it tells us that we are reading buff, and it's a string, and we also write to it. It has a read-write effect. And we read something called name, and that's a string. And notice there's no transformers, we haven't used lifts, we don't have to do lots of compositions of lifts. And so the technique is essentially to embed an effect system into the monadic typing approach. This gives us more information, gives us rich information about the effects, and it helps us with composition. So, what's the technique? So, Gifford and Luxon in the 80s introduced the effect systems, and there's been a lot of work on this. Classically, they're syntax directed, so they describe them with along with a type system because it has a similar shape. And the traditional one is to look at memory and have a set of effects. So if I have this program with a put and a get, then I do this analysis and I see that I'm doing a read and a write. And this is used in lots of compilers for doing optimizations and things. So the general structure, I'm just going to be thinking about first order programs here, no abstraction, is that for let binding I have some effects F and G, and those are combined with some join operation of a lattice. And when I use a variable, then that's a pure thing, and then I have this sub rule which I can use to over approximate effects. So this is just a little characterization of the traditional approach. Now in 2003, Phil Wadler and Peter Tiemann had this really cool paper where they united this effect system approach with monads and looked at the operational semantics, looked at the syntax, looked at the type systems, and did some really nice proofs and showed how you could sort of put them together. So you end up with a system like this where instead of having this effect annotation which isn't in the type, it's something else, it goes onto this monadic type constructor M, which takes two parameters. It takes an effect annotation, and it takes the type of the computation. So you see this has the same shape, has the same feel, but now we're back in the monad world. So this was a good paper, but it didn't consider the semantics, the way that we embed this into a language denotationally or in a functional language. So we can do something similar. We can marry effects and monads semantically using something called a parametric effect monad. And CounterMonad showed this at Popple this year. We also called it independently an index monad, but that's a bit of an overloaded name, so I'm not going to use that here. So we have one of these binary constructors for the monad, and it takes this effect annotation, and actually this is going to have some structure, and I'm going to show you the full definition in a moment. So we're going to use this, we're going to put it in Haskell, and we're going to use GHC's awesome type system features, which we were hearing lots about yesterday from Stephanie, and we're going to leverage lots of the latest goodies to use this to embed the classical type system approach into Haskell. Okay, so this is the type class I'm going to be using. This is the parametric effect monad. This should be pretty familiar. The shape of it is very similar to our normal monad class. The operator name is the same, but now we have a binary constructor M, and its first parameter is something of kind K. So K is going to be our domain of effects. And then we have these two type families, type level functions. One gives us the unit effect, and the other tells us how to combine effects together. It's called plus. So when we return, we annotate our effect monad with the unit effect, and when we do bind, we have something with S effects and something with T effects, and they're combined by plus in the result to get ST. Now I should point out that for every effect annotation I, it's not necessarily that we have a monad, it's not like a family of monads, but there's this sort of monad-like structure that's provided, but with these effect annotations sort of sitting over it. And we'll think a little bit about sub-effecting. I'll mention it a bit later, but there's also this class as well that tells us how to over-approximate effects. So the unit and plus together, they form a monoid, which gives us this monad-like flavor. So where does that come from? If we take the normal monad laws, it's just these are just the standard ones, and then we use them with our parametric effect monad, then we get these types. And we want each side of these equalities to be equal, so these types need to be equal. And I've just removed the extra m's there in the families. So this shows us how we want it to be a monoid. That has this sort of monoid-like behavior on our annotations. Right, so first example, reader effects. I'll go back to state, but it's more complicated to show you, so it's easier just to go with reader. So reader effects, it's like having some memory that we can read or some global variables. And we want to have terms that are something like this. We ask for some different things, x, y, z, and then we end up with a type that says which things that we've read and tells us the types of those things. And we're going to use sets in our type system. So we're going to have a set of variable type pairs. Now I'm using this little colon arrow thing. This is a sort of like a pair showing you what the type of variable is. And I'm using something called type level symbols, which is a way of basically having strings in our types, which is very, very convenient. So I can introduce one with this var type, which you'll see around. So I might write things like this. There's a data constructor var, which has type green var, and then you put the name in, which gives you this type level symbol. Don't worry if that's like a little hard to digest. You should just be able to see there's going to be these type level strings that give us the names for variables. But what do we do about these sets? This is a bit tricky. They're a container that's unordered without duplicates. So how do we do this at the type level? So we're going to start with type level lists of these pairs, of these mappings. And then we're going to normalize them by sorting them. So sets are unordered, but we're kind of normalized by actually sorting them based on the symbols. And then we're going to remove duplicates. And this is facilitated by by data kinds and closed type families, which is totally awesome. I'm very excited. I've been waiting to write this paper for a long time, but it really needs closed type families, and I'll show you this definition. So thank you so much to the people who did this work. I mentioned that. So we have this GADT for set, and it's indexed by the kind of lists of types. So this has really nice syntax as well. We get these little constructors that look a bit like lists, but they have a little tick in front of them at the type level. And this should be familiar as the sort of heterogeneously typed list construction. But we're calling it set because we're going to use it like a set. So when we take the union, what we're going to do is we're going to append to the union of two set things is going to be the append, and then the sort, and then the nub, which removes duplicates. And the sort is based on the bubble sort for simplicity, sorting based on the variable parameters. So you can see that in the paper. So here's the nub function. It's a closed type family. And if you squint a bit, it should just look like the normal nub function on lists at the value level. But because it's closed, we can now do pattern matching on the types. And in this third pattern, we're testing the quality of two types. So when we've got E next to E, then we get rid of that, and then recurse, we call nub again. So this is great. This is really lovely. So thank you for closed type families. And then the last clause is when they're different. So these are matched in order, and we go on and we remove the duplicates. So let's see some little programs. Here's the ask, the type of the ask function. We give it a variable, and then this has the effect of records the type of the variable there. So if we do, we ask for the name, and then we return the name, return some string plus this, then we get our name effect. It's pretty straightforward. So let's do something with a couple more variables. I'm going to ask for the name, and then I'm going to ask for the age, and show this, and this gives us, this is actually inferred as well, GHC can infer this, which is nice, and it tells us what our reader effects are. And then I can run this with some piece of data. There you go. So here's another example. Oh no, sorry, this is actually showing you the instance for reader. So readers are just exponents, so if I'm reading R and getting an A, it's just a function from R to A, so I'm going to sort of simplify it by writing it like this, so I don't have to write too many constructors. So the unit effect is just the empty set, and I just pattern match an empty and return the thing, return the value I'm returning. And for plus, we take this union, and so if you look at I put the signature for bind in here. So we have a computation that requires S. It's going to read some S things, and then we have an arrow, applies the arrow that's going to read some T things once it's done. And so the computation we get out reads the union of S and T. So this lambda here, the actual definition, takes ST. This is the set with all the S things and all the T things in. And so it splits it apart into these separate variables, which are then passed to the first computation, then the second computation. So split has a type a bit like this. It's defined using a type class. Again, details online in the paper. Actually, there's some other things that actually go on in this class. We also use a constraint family for extra flexibility, and it's used here. But that's pretty straightforward. And then the ask, the definition of ask is we just have a singleton set that we're reading. We're reading a singleton set of this var v. Okay, now for another example that's not sets. A lot of the examples in the paper and in the library are sets, but they don't have to be. So I call this the CounterMonad, and it actually appears in a paper in 2008 by Nielsen. And we annotate our monad with a natural number, which actually has no value level meaning. It's just an annotation for us. And when we return, we annotate 0, and when we do the bind, we take the plus of the two annotations. And then we have this operation called tick, which sort of counts 1. And we can use that to do something like counting steps in an algorithm, or number of calls to a server, or number of times I use some resource. So this is really cool because you can do things like verifying the complexity of the map operation. So I've taken map, and I've just, instead of writing the normal recursive one on lists, I'm doing it on some other sort of data structure, and I've used the do notation, so I've made it sort of monadic. And so I'm going to take in f of type A to counter tb, so it's a function that does t things. And this is defined on sized vectors, so I'm taking a vector of size n. And then this is the type that we get that type checks this function, where we count n times t to get the vector of n of type b at the end. So this really, like, if this type checks, then we've done the correct implementation of map that goes through and looks at every part just once and calls f once for every element. So that's pretty neat. There's lots of other examples in the paper, so I'll just give you a little tabulation. So M is the effect parameterized monad, K is the effect domain, unit is the unit effect, plus, and then there's the sub. So for reader, we had these sets of symbol to type pairs with the empty set and union and subsets. There's also something that's similar for the writer. Oh, I should say that for the writer, the types have to be monoid, so it's like the normal writer monad, but we have lots of them together. This has the same operations. There's something called the update monad, which is like having a cell which you can choose to overwrite or not. So it's annotated by maybe, so if it's a nothing computation, then it doesn't overwrite the cell, it doesn't rewrite the cell. And if it's just of some type t, it means I'm writing this type t. So it has a sort of join operation and nothing. You can always pretend that you have updated the cell, and that's the safe thing to do. So there's state, which is the really kind of cool one, which is similar to reader and writer, but now we have this little extra data type that tells us whether we're reading, writing, or doing a read-write. And then it has a special union, which I'll show you in a moment, which is similar to our previous union, but when we have a read and a write to the same variable, it squashes that together to a read-write. So it's not just pure union. There's the counter, which I mentioned. There's also something which has this sort of, if you look at the sub, here we have a superset relation. This is an effect system for tracking data access on an array. So there's lots of different kinds of array computations, like convolutions, and in convolutions you have this relative data access pattern. And this effect system tracks the access pattern inside your inner loop of your array and gives you a sort of set of the indices that you've accessed. And then you can write signatures against that, saying, well, have I actually implemented my kernel correctly? And there's a bunch of macros that I show in the paper for like symmetric patterns and forward patterns. But there we actually want the superset for approximating effects. So that's sort of slightly different. Okay, so state briefly, I showed you it at the beginning. It has get and put operations like this, so I can get variable v, and then it has the read effect. I can write variable v, and that has the write effect. And the nub function is really similar to before, but it has this extra clause that says if I have a variable, called k, that's not a very good name, but and they have the same type, but they have different effects, s and t, then turn that into a read-write effect. So this basically just makes our types a little bit smaller, because it's quite often that you have bits of a computation where you read a variable and write it. So rather than having to have a read and a write for the variable, then you can just do the RW effect. So the paper has lots of examples, also talks about effect polymorphism, also talks about coeffects, woohoo, and how implicit parameters in Haskell are actually a coeffect system, and you could do a similar thing to embed coeffect systems in Haskell, well, certain kind of coeffect system using the Codu notation. You can find all the details. Sub-effecting is mentioned too. Just a quick word, there are other ways to get effects-style systems in Haskell. One kind of well-known technique is to make a type class for every operation that you're using, and then use constraints which act like sets as your effect system, which is pretty cool actually. But you still have to end up implementing those with transformers, and our approach is much more general. You have much more flexibility about what you do with your operations. You can have like the union of read and write variables where you make an RW. You can have the maybe annotation, the plus, and it's sort of a more flexible approach. So in conclusion, we've heard a lot about effect handlers, and I think they're really great. And I feel like this is some sort of intermediate between the two. So we have monads that are okay, but they're a bit sort of stubborn. And this is somewhere between the flexibility, the approach of monads and full flexibility of effect handlers. But I also think that you could use this as an effect system for your handlers. So perhaps we could embed this into the work of Kamar, Lindley, and Ori, where they have handlers in Haskell, but they don't track the effects, the operations so well. So you could use our set-based approach. But this is our approach is quite nice because it just embeds into monads in the normal way we're already working with effects. So you don't need any extensions and macros. So maybe it's a sort of step towards more flexibility. So just a little reflection on types. So GHD types are amazing, but there's still lots of, like, if you look at the code, there's lots of points where there's a value definition and there's a type definition, and they're essentially identical modulo the change in syntax, like appending lists, which is a shame. You know, if we were using Agda, you could just write it once. So maybe there's some things that could be done there. Sometimes you need some extra signatures to make sure that the type checker can figure things out. Like the map example, you just have to give that signature. It can't unify to the multiply itself. Lots of other things work quite well with inference, but occasionally you need to put some hints in. And it would be nice if there was some sort of native type level sets like this, native type level lists. So maybe ICFP 2015, there could be some solutions. Okay, thank you very much.
Questions?
Dominic, you've said that the type level unit and plus need to satisfy the monoid laws, but you have no way of enforcing that. No, you don't. Again, it's sort of up to you. Yeah. And do you ever end up in a situation where the type checker needs to know those laws in order to type check something?
Yeah. So usually it's fine, but with the state, it has a bunch of extra sort of things on the inside to do with how it pulls apart things that you've read and written and threads them through. And sometimes it gets a little bit stuck with all those. No, I think it's mostly fine. Yeah, I haven't had any serious problems with it. With the set examples, at least it's okay. But I can imagine there might be some things where maybe you had lots of stuff going on and you gave a type signature and it couldn't quite figure it out. Unit and associativity seems okay.
I have a comment and a question. The comment first. I'll tell you what I usually told my students: never, ever, under any circumstance, use bubble sort.
Hey, it's at compile times.
Okay, but it still uses CPU. So my question, so say that you have read effects and one part reads variable x as a bool and another one as int. Where does that show up?
You'll get a type error saying that it can't take the union of the.
But the way you showed us the nub, that would have put the effects in twice, I think. Once as a. It didn't show us the sort.
I think the sort figures it out. Yeah. I'm not sure. Yeah, I'm not sure.
The questions have all disappeared, so maybe I'll try.
Maybe they wanted to ask that question. Yep.
Given two sorted lists, you append them, sort them, and then number them.
Yes.
Why don't you just merge them?
Yeah, that would be an optimization, and you could add that to the library.
And then you don't need bubble sort.
Yeah. Again, I just did the simplest thing to make the paper kind of easy to sort of read and get through.
Yeah, but harping on the issue that Lennart raised, shouldn't it be a partial monoid then? I mean, it's not a total operation.
No, well, you could give lots of cases for your type family and just not give them all, and then the partiality would come out as, oh, I don't know, I don't have an instance of the family for these types. So yeah, that they can be partial. Yeah. Sometimes that might be a plus, because then you could start embedding program logics.
So I haven't been to the Haskell workshop for a couple of years, and I have to admit at the beginning of your talk, when I saw these types, I was under the impression that perhaps you had extended the language or were doing something else, but no. So, I have to say, and I mean this in the best possible way, but I feel like I blinked, you know, and we went from you know, types which were sexy from Simon's talk years ago, to types that are positively slutty. In the best possible way. I'm glad you were able to take advantage of that type sluttiness, because it seems like it's gone quite well.
Well, our presentation and paper is maybe slightly tongue-in-cheek. It's like, wow, look what you can do, but wow, look what you can do. Yeah, it's not the best. Actually, at the user code, when the user code you're writing, it's actually not that bad. It's inside the library that you have all these like horrible, like, oh, I've got loads of type families and stuff. So what the user writes when they're using these effect monads is actually not that bad.
Last question, cool?
Okay, so I have a similar impression. So I was surprised at your map example with the counter thingy, that the time suddenly shows up in the types. And how is that type check? And are there any practical restrictions that you, I mean, does it work because it works, or does it work because you just did the right thing?
It works because it works, but well, no. You do just do the right thing. The definition of multiply is quite similar recursively to the definition of map. I think that's probably why it unifies okay. So actually, I did cheat slightly in that I described this using the nat kind. That actually doesn't work. So I have to use my own rolling of nat. So if you use nat has a plus and it has a times, but the type checker doesn't know about the rules enough. So there's actually something called CounterMonad in the library, which is using the normal approach. You write it inductively yourself for the plus and the times, and then it works. Thanks.
Okay, let's thank Dominic again.
Cool.
So we have a short 20-minute break to stretch your legs.
You mean as opposed to sharp?